Our next topic is 8.11. So we have a volume with something called the washer method. Now we are going to revolve around the x or y axis. So let's go ahead and take a look at what the difference is between a washer and a disc. So a disc would be like a coin, something solid. A washer is an object that has a hole in the middle. So you can guess what we're about to do here. We are going to create 3D objects that are not completely solid. They have some sort of hole or gap in them. So to see this drawn out, let's go ahead and talk about the volume of the solid generated when the region bounded by the graphs of y1 as square root of x, and y2 as x to the third from 0 to 1 is revolved around the x-axis. So in previous lessons with the disk method, we revolved a single area around an x or y axis or even other axes like we learned in 8.10. This time we're going to have a region that's bounded by two different graphs, and so we need to look to see what kind of shape this will make. So let's first draw a picture. So square root of x and x cubed from 0 to 1 looks something like this. So now we would like to imagine what this looks like when we revolve it around the x-axis. So if you imagine taking this shape and revolving it around, it is no longer solid. It has this hollow piece in the middle. So the only solid piece here is this piece that goes around. And I guess if you'd like to imagine this piece also, so it's going around, so it is creating something solid on the outside, but then it has this inner gap. So your textbook does have one example of this on page 408. It has a visualization, so imagine taking this area and rotating it about the x-axis. You can see here that you have something solid, but it has this gap in the middle. And so that's why we call it disc. I'm sorry, that's why we don't call it a disc. The disc is solid. A washer has that hole in the middle. Next thing we need to do is to draw a slice and figure out what the volume of the top slice is and what the volume of the bottom slice is. So you can see here that my top curve is square root of x and my bottom curve is x cubed. So if I want to draw, imagine a volume of the top slice, so I'm going to call it V subscript top. We are still going to use the same formulas from previous topics. We're going to need pi. We need our boundaries. So because our slices are vertical, they are perpendicular to the x-axis. Imagine drawing a little slice here, taking that out. We need the boundaries on the x-axis. So we are going to go from 0 to 1 because the problem told us to. So imagine again here we have top minus bottom. So we're just going to look at the top portion right now though. So the radius of the top slice was square root of x, and we need to square that. So in other words, that's pi 0 to 1 of x dx. Now let's go ahead and take a look at a volume of our bottom piece. This one, the radius is x cubed, and we need to square that. So imagine, if you will, we have this top slice. If I were just to take the integral of this piece, I would have a solid region. If I were just to take the integral of this piece, I would again have a solid region. So how can I somehow get the volume that I want, the slice that I want? Similar to the previous topics, we need to subtract the two. And in previous lessons, we saw that it was okay if we well, in certain problems, it was okay if we flip-flop the order because we would eventually square it. And so if you subtracted out of order, it was fine because it would be taken care of since it was squared. This time, however, it does matter. When we subtract, we do need the volume that's on top. We do need that one written first. And then the volume on the bottom, that needs to be written next. All right, so there's a couple ways to tackle this. You can go ahead and find the antiderivative separately and plug in 0 to 1, 0 to 1. Or if you recognize one of the integral laws, that when you're subtracting with the same boundaries, you can go ahead and subtract together in one integrand. All right, and just a little bit of practice here with finding your antiderivatives. It'll be x squared over 2 minus x to the 7th over 7 from 0 to 1. So if you plug in 1 and 0, you would get 1/2 minus 1/7, which if you do that math, you will get 5 pi over 14. So let's go ahead and take a look at the formula for this new method called the washer method. So this method is used when you have a region that's bounded by two graphs, so you're going to create some sort of hole or gap in your solid. Disk method is if you have a single region being revolved around and there's no gap. To help you visualize the gap, I suggest drawing a visual, drawing something to help you see it, whether you need to use washer or disk. So for the washer method, it's very similar to what we did with disk method. However, we do need to subtract, and order does matter. I called it the outside radius. So in other words, this was the top curve, whatever the top curve was, and then minus the bottom radius. I'm sorry, the inside radius, which is called also the bottom curve. Okay, this next example was part of a free response question. You can use your calculator here. So let R be the region in the first quadrant enclosed by the graphs of y equals x squared, and for x, find the volume of the solid generated when R is revolved around the x-axis. All right, here's x squared, here's 4x. If you need to, grab your calculator to find where they intersect, or set these two equal to one another. I'm doing a little bit of algebra. Factor out an x. So you see that they intersect at 4, and then to find the y value, you just plug in 4 into either, you'll get 16. Okay, to help us visualize what's happening is I'm going to rotate this around the x-axis. So again, we have something similar to before, where we have this sort of cone-shaped object lying on its side. If you maybe want to visualize it this way, it's almost like a tent with really solid, thick walls, and there's a gap in the middle here. So let's think about what our outside radius is, or in other words, our top y, and then what our bottom radius is, otherwise known as our bottom y. So here, if you draw the slice, our top radius was 4x, and our bottom radius is x squared. So let's go ahead and use our formula. Again, let's look for our boundaries. So you'll notice the slice is perpendicular to the x-axis, so we're going to have a change in x, which means we need to find the x values. So our solid goes from 0 to 4. Go ahead and square the outside radius minus the inside radius dx. Now, a lot of you have been writing something like this on your paper in previous lessons. make sure to have a parentheses on the outside, because if you don't have that parentheses, that just means you're multiplying dx times this one. You need to have the parentheses here to show you're multiplying dx to everything. All right, and this one is calculator active. So you can go ahead and plug into your calculator like this, or if you want to clean it up a little bit before doing so, you can. $428.932.